So this is obviously an experiment that we're going to try to do here. The basic idea is that roughly 10 years ago, there was the famous 1995 conference at USC. And we thought that it's timely to sort of take a look back of what has been accomplished and what remains to be done. Also in the light that, as Nima explained in his talk, in the next few years, there are going to be exciting experiments that are going to come up in line, and we want to know what the theory, if anything, can say about them. So when we started thinking about this, is how are we going to do this? There are 440 participants, and there are obviously not all of them can talk. So we decided that we would make some panel discussion. So the first thing we had to do is to choose the name of a person that would moderate the session. So what we did is we chose Steve for two reasons. The first one is because he's a person that everyone respects. And number two, more important, is is someone that everyone fears. So to keep the fear going, I'm going to give you this stick to keep the crowd under control.
Thank you, John.
Yeah.
So this is for you. I'm used to being hit with those.
So essentially, without further ado, please, Steve, take it away.
Well, it's nice to know that the abuse one hands out as a thesis advisor stays with a student for years and years. Well, thank you all for coming this evening rather than being in the air-conditioned comfort of your hotels, watching movies or something like that, and we'll hope we'll make this entertaining. But that job will be yours as well. Is the mic off? Or I need to be in front of it? Okay, is that all right? Well, we titled this panel discussion, The Next Superstring Revolution. And of course, what we're referring to is this history of our subject that kind of a broad brush history that we repeat to each other, that in 1984 there was a big revolution. The field went to being populated by a few pioneers to the hundreds of people that are sitting in this room. Well, some of you weren't sitting in this room then, but you get the idea. And then in 1995, there was another big revolution, often called the duality revolution. And then, of course, people in this subject in this room are not very good at analyzing data as a rule. But I think all of us have done the calculation that the spacing between these two revolutions is about 10 years. And as Jaume mentioned, it's about 10 years since the last one. So it appears that we're due. And that's sort of the text of this panel, is to try to talk about precursors that we can spot to this impending revolution. So let me make a couple general remarks that might be an aid to spotting these precursors before we get along to the panel discussion. The first is that in the previous revolutions, many of the crucial ideas already existed in the literature, sometimes for years. And secondly, these ideas, by and large, were either ignored or actively dismissed by the great majority of workers in the field. So I think it's a very good bet that many of the crucial ideas that will come into play in this next revolution are already out there on the archive and are either being ignored or dismissed by most of you. Okay. Now, unfortunately, this observation is not that useful in making predictions about what will be the next revolutionary ideas, because most of the things on the archive that are ignored for a very good reason. It's a problem of separating the wheat from the chaff, if you will. Well, that brings me to the landscape. These ideas have been clearly a very exciting part of our subject in recent years. And if environmental selection proves to be correct, this will be a revolution in the way we think about physics by any measure of the size of a revolution. So it might well be, if this is the way things go, that we'll look back on this time from sometime in the future and say that the third superstring revolution happened 5 years early. Okay? And I'm afraid this will be just another example about how things in the landscape make prediction very difficult. All right, well, finally, there's at least one thing that we can say with some confidence, and that is in a little more than 2 years, the LHC is going to turn on. And this machine will deliver, as we've heard today, the most exciting particle physics that has been found, or at least it's likely to do that, since this 1984 revolution in string theory. This and the possibility of new astrophysical data make for the real possibility that this next revolution we're talking about will be in part data-driven. And that will be revolutionary indeed. Okay. All right. So now let me tell you what's going to happen. Each member of our distinguished panel, which represents, I think, a very nice sample of the leaders in the field, will say a few words about these subjects. We won't have any questions between the presentations. And then afterwards, we'll open things up to the audience as a whole. And I really invite and encourage you to give your ideas about what the crucial ideas are that will drive us forward, questions for the panel. And also, I would encourage you to be impolite. All right? We want there to be, strong interchange and elaborate courtesy that's common, although by no means universally common in our field, is often a detriment to that. Okay? Now, I must confess that I've endeavored, rather secretively, to try to limit the communication the panelists have had with each other about what they were going to say. Okay? And my purpose in this was to enhance the freshness and the spontaneity of their presentations rather than reaching some consensus. But that means I'm to blame if there's any overlap in what they say or any lack of coverage in the subjects. Of course, I would like to take credit for the brilliance of their presentations. And I hope that you will give me that. All right, so without further ado then, we're going to start, and the first panelist, and we're going to go in alphabetical order since I couldn't think of any more suitable one, will be Rafael Busso. Well, since you've applauded for me, let's cancel the applause for everybody else until the end of the session, okay? All right.
Okay. S. Do you have a pointer?
Oh, yeah. Here's a...
That would make it interesting. Perfect.
Did they write one?
Shannon is next in there. I'm usually not third.
Okay. So I'd like to start with a brief wish list. I am supposed to hold this thing. Okay. I'd like to start with a wish list of some questions that I hope will be answered by string theory someday soon. And it's centered around the problem of describing regions where gravity completely dominates the dynamics over all forces. That includes cosmology as a special case, and it also includes the famous old story of trying to describe the infalling observer infalling into a black hole. I think this is sporadic. Okay. So we have learned very little from string theory about either of those topics, at least not at the level of rigor that we're otherwise used to from string theory. In particular, I'd like to know what this infalling observer will experience when they hit the space-like singularity in the center of a black hole. I'd like to know whether physics continues in any sense there and what are the degrees of freedom that describe it. A GR intuition would tell you that space and time are treated on an equal footing and that there's no reason to believe that time will hold up when space breaks down. The quantum mechanics intuition will tell you that time is a key evolution parameter in quantum mechanics that we can't do without. So it will be interesting to see what gives. Does time survive? If it doesn't, is that an indication that quantum mechanics is just as emergent and no more fundamental than we expect general relativity to be? So far, certainly there's been no indication that quantum mechanics needs modification from string theory. But I wouldn't trust that trend until we know how to take string theory into a regime where gravity is dominant. So what's been keeping us away from answering these questions? I think we all could add many points to this list. I'll just review what probably many people agree on. We're too much addicted to supersymmetry and to having fixed assumptions about how our spacetime should behave at large distances, fixing the asymptotic conditions, having a boundary, which in itself almost precludes having a closed theoretical structure, since then who makes up the rules about what gets sent in from that boundary? And of course, connect with supersymmetry, where we're usually in the unfavorable companionship of a time-like killing vector that prevents us from really doing time-dependent backgrounds well. But I think deeper than that, we can ask, okay, let's hope that the next superstring revolution is going to answer some of these questions for us. But what's more likely to happen is the next superstring revolutions will answer other very interesting questions, many of which we wouldn't have thought of asking. And what's a little bit frustrating about that is that it's hard to tell, as we sort of random walk through this beautiful, rigid structure we call string theory, when that random walk is finally going to take us to the place where we can answer these questions. And so what we're suffering from, I think, is that the way that string theory was handed to us was by a green book by Green, Schwartz, and Witten, and not by the usual way of arriving at certain physical principles that you want to incorporate into a theory, and then developing the theory accordingly. So we have very little guidance, other than by the rigidity of the structure itself. And so my out on a limb prediction, which I guess one should make at least one of today, is that as the subject develops further, such guidance from general principles is going to become more and more important. Okay. And it's going to guide us in the right direction so that we don't explore things that aren't terribly relevant for the real world. Just to try and attempt a very primitive illustration of what I have in mind, there is one general principle that some of us believe is important for quantum gravity, and that is the holographic principle. And so far, it looks like string theory is holographic in a sort of general sense, but there's been very little interaction between the general reasoning that has led people like 't Hooft and Susskind to recognize the holographic principle and the way that we do string theory. It's really very much a split screen. We have on the one hand this beautiful non-perturbative definition of gravity in asymptotically anti-de Sitter spaces that seems to capture this holographic idea of having the right number of degrees of freedom, scaling like the area. It's precise, it's rich, but it's obviously totally unrealistic. On the other hand, we have entropy bounds. They're no theory of quantum gravity. They're simply a pattern that we've started to recognize, that the entropy on null hypersurfaces is smaller than the largest cross-sectional area on any such null hypersurface. And the strengths of this side are the weaknesses of the other, and vice versa. So this story, it's not a theory, it's a semi-classical pattern that's been observed, but it has the advantage of being both empirical, it appears to be true in the real world, and very broad. It works precisely in those regimes where string theory has the biggest problems, when gravity is dominant, when there's no supersymmetry. And in fact, it makes its strongest and most surprising statements in that context. So what, for example, if we try to get these two sides to join forces? If we try to understand what we can learn in the context of ADS-CFT by not thinking about it, as we accidentally can in this context, as a space-like projection out of one dimension, but taking literally the idea that the bulk and the boundary are supposed to be connected by null hypersurfaces. There's been very little, as far as I know, in terms of trying to extract as much as we can from the ADS-CFT correspondence to get the best starting off point, the best bridgehead for continuing on to less favorable backgrounds. There is a paper by Sahakian where he points out that the RG flow along a light sheet away from the boundary admits the definition of a C function whose corresponding C theorem is basically guaranteed by the focusing theorem of light rays in general relativity. So there might be some nice correspondences and observations there. Another idea might be that if we need to face this horrible space-like singularity at the end of time, we could have a lot less trouble when we slice space-time into null hypersurfaces, because that puts time-like and space-like singularities pretty much on the same footing. Time-like, we've already had some examples of how to resolve those. They become a place on your slice. Unlike in a usual slicing, where you hit the whole high curvature region everywhere at once, all at the same time, and time seems to end. So those are my suggestions for just an illustration of what I mean by getting some guidance. Thanks very much.
Okay, our next speaker will be Shamit Khosru.
All right, well, I'm afraid my remarks will be pedestrian compared with Raphael's beautiful presentation, but I promise you at least I'll be brief. So Steve's task to us is to talk about revolutions. So here are my pedestrian remarks. As far as I understand it, revolutions occur when important problems, sometimes they've been well known to us, often in string theory they haven't been well known to us and are recognized only after the fact, are solved. And so what I'm going to do is just describe some such problems. They're mostly pretty obvious. And then describe a question briefly that several of these problems suggest to me. The most obvious problem that our field has been coping with since the late 60s and then into its new incarnation in the mid-80s is problem one. Can we find observable signatures to characterize wide classes of semi-realistic string vacua? We've heard many talks in this conference already about how there are different classes of constructions which incorporate realistic features of the world. None are completely realistic as far as we know, but how on earth could you test them in a characteristically stringy way? A related issue, at least from any approximations we currently understand, there seems to be a landscape of potential late time vacua, things that have mild time dependence. They're not guaranteed to emerge from any sensible full cosmology. Does a full string cosmology, which we have yet to find the language to describe, put any useful measure on this, or in other words, tell us that this landscape of potential late time vacua is or is not an important concept? And a third question, and this I think dovetails to some extent with the issues Raphael was discussing, is that we have very precise definitions of simple string backgrounds, and in particular those with spatial infinities, by ADS-CFT, or in cases with more than 5 non-compact dimensions in Minkowski space, by matrix theory. But most of the backgrounds a lot of us care the most about, for instance, de Sitter space, lack such infinities. Do we have the tools now to give precise precise definitions of such backgrounds of string theory? And what are the new concepts that we need? Now, the first problem I mentioned, the most obvious one, the one you've learned from youth, is to me the most ambitious one, if one can make progress on it, but I really have nothing useful to suggest. And there were nice talks, for instance, by Polchinski and Witten with interesting ideas, and there's plenty of room for more such interesting ideas. We won't find tests if we don't look. But I think problems 2 and 3, which are less immediately ambitious, both suggest that we try to attack the following question. This question is not obviously well-defined. I'm sure some of you will think it's obviously not well-defined, but I think it brings the right associations with it. And the question is the following, stated pretty vaguely already. What are we to make of string theory compactifications to 0 + 1 or 1 + 1 dimensions? Okay, by which I mean, for instance, string theory on a 9 torus, or on a Calabi-Yau fourfold times a circle, or string theory on an 8 torus. Now, why am I asking this question, and how on earth does it relate to the problems I outlined? In the context of physics without gravity, there are well-known theorems assigned to the names of people like Coleman and Merman and Wagner that say that strong infrared fluctuations of fields, okay, in low dimensions, cause the formulation of physics to change. That is, instead of choosing a point in moduli space, assigning to it a Hilbert space and a fixed Hamiltonian and doing normal quantum mechanics, one somehow has to do a quantum mechanics on the moduli space, not assign a different Hilbert space to each given point. Now, our experience with the connectedness of the space of string vacua, okay, which is not yet decisive, but it's pretty suggestive that we're really exploring one big connected structure, suggests that fluctuations may, in fact, connect dynamically many such models when you get to low enough dimensions. And quite conceivably, if you really formulated one such background, you would succeed in formulating all of them. That either says this is a great thing to do or it's impossibly difficult. Now, if one succeeded in doing such a thing, or at least turning it into a reasonable physical question, the resulting object, which may be a wave function or wave functions, could, for instance, be natural measures in what some of us call the landscape, but there could be other spin-offs. Now, I should say right at the outset, the same idea has occurred again and again in different contexts, and that's another reason why I think it's something we ought to revisit every now and then. There were many related ideas explored in the past. One of the earliest attempts to do string theory cosmology by Brandenburger and Vafa used in a crucial way compactification on a 9 torus. Greg Moore, sometime right when I was entering the field, suggested that compactification not only of all spatial dimensions, but Greg is very ambitious and also compactified time, is a natural place to look for the master symmetries that might control string theory. People like Guth, Linde, and Vilenkin in a completely different context have studied the measure problem in eternal inflation, and that feels to me like a very related set of issues. A few years ago, Waddy Taylor, maybe others also, suggested that open string field theory might be most fruitfully formulated on T9 if one wants to use it to define our theory. There are works by Karch. Now, I don't know, given that people have thought about this issue on and off in different contexts for 15 years, that we're ready to really make progress on this kind of question or to even formulate the question properly. But surely if we did understand this subject in any way, it would help with the problems I called 2 and 3. Thank you for your time.
So our next speaker will be Juan Maldaceno. He's got to turn on though. You can.
Okay, so well, doesn't seem to be working. But okay. Okay. Yeah. Well, I hope in 5 years we will be using a better program. So first I thought about sort of simple questions for the next 5 years. I think one of these questions is to understand better how strings emerge from gauge theories, from strongly coupled gauge theories. It would be nice to have a method that gives us, given a gauge theory, we find a two-dimensional worldsheet theory that describes strings for that particular gauge theory. I mean, a lot of progress has been made in understanding this problem for n equal to 4 Yang-Mills and other theories in terms of spin chains and so on. But we still don't have some method that would give us the Hamiltonian or the Lagrangian for the two-dimensional worldsheet theory once we know the Lagrangian of the four-dimensional field theory. So hopefully this might lead to understanding the pure Yang-Mills theory, or finding the string dual of the pure Yang-Mills theory. And I think this would be a very interesting class of string theories with Ramon backgrounds that could be relevant for many other problems and maybe even relevant for phenomenology. Another sort of related question is to understand better the ADS regions of the landscape from the field theory point of view. So understand what's there and why are there so many different vacua, or what's the generic behavior of a strongly coupled gauge theory or field theory with large number of degrees of freedom. So do most of them have a curvature which is of the order of the Planck scale, or do they have a curvature much smaller than the Planck scale, and so on. So there are many questions there that maybe that seem within reach for the next 5 years. Another problem that I think might be solved, or would be nice to solve, is to find a simple solvable model for the two-dimensional Lorentzian black hole. I mean, I chose this two-dimensional case because in that case we can, at least when we don't have a black hole, we can solve the string theory exactly, and we can solve the field theory exactly and compare to string theory. And it might be a good place to understand some of the issues of black holes, like the interior, etc., etc. Maybe there is some other solvable model for black holes. Maybe it's not the two-dimensional black hole, but it's some other black hole. it would be very nice to understand these issues with the black hole interior. Now, I'd like to now pose some more ambitious questions. So one of them is whether there is a wave function of the universe or whether this is a useful concept. I mean, if there is, how do we pick it, and whether there is some kind of Schrödinger equation for it. I mean, my feeling is that, well, this has been said by many people, but the feeling is that in string theory we are still like in the old Bohr's atom model, where basically one can treat only integrable systems, except that in our case integrable would be replaced by supersymmetric, but we can only treat supersymmetric situations or situations which differ by a small amount from the supersymmetric situations. But maybe once we found this Schrödinger equation, we'll be able to treat quantum gravity in a much better way and in the general way. Now, I think that from ADS-CFT we have some hints that there is a concept like the wave function of the universe, and that is unique. Now, what I have here in mind is that if you think about the Euclidean version of ADS-CFT, you have a Euclidean boundary which you think that exists there for large Euclidean time. And if we expand the wave function of the universe, we'll have a leading tail, and the prefactor of that leading tail is the partition function of a field theory, and so we can compute at least this piece of the wave function. And since the answer for this problem is unique, one would think that this is a hint that there is a unique wave function for the universe. So that's a very encouraging fact. However, if you start thinking that about ADS-CFT and you think that, well, you can deform the field theory in many different ways, it seems clear that you can probably get to all possible field theories by, let's say, deforming n equal to 4 Yang-Mills or related theories, by adding mass terms, flow, etc., etc. And what this would be saying is that all possible field theories actually would have some quantum gravity dual. So in a way, this wave function, even if we found it, it would contain the answers to all possible questions. So by expanding it in regions with large exponential behavior, we would find the partition function for all possible field theories. Of course, you would need to know how to expand it, and so you really need to know the question. So the wave function of the universe contains the answers to all questions, but of course you need to know the question. Otherwise, you'll get answers like 42, and you don't know the question. Now, given the fact that I find this fact a little discouraging, that the fact that this wave function would contain the answer to all possible field theories, because it seems so general and so big an object that it would be very hard to compute. On the other hand, it's very hard to think that if we have a theory of quantum gravity, there should be a wave function. Otherwise, we have to give up the usual concepts of quantum mechanics. So I guess some of the speculations are that the wave function of the universe might not make precise sense for an observer in a closed universe or in a cosmological situation. Because in some ways, the wave function seems to contain too much information that is not as accessible to this observer. And as happened, let's say, previously in quantum mechanics, so information that is not accessible is actually information that is not there in the theory in the first place. So maybe probabilities are not sharply defined as they are when we have a wave function, but even probabilities themselves are somewhat uncertain, because the observer that lives in a closed universe cannot repeat the experiment. So perhaps the right concept is not the wave function. We need to change some of our concepts about quantum mechanics. Well, thank you.
Our next speaker is Joe Polchinski.
I don't have any. I don't have anything really. I'll just stand up then. Okay. Yeah. Well, I really don't like making predictions. I feel like my approach to physics is kind of a random walk, where you make progress mainly by taking as many steps as possible, not have any overall sense of direction. But I guess I'm signed on for this. So Steve and several people have said to me, so Joe, what are you going to say about the anthropic principle? But I guess I took his instructions too literally to talk about the next string revolution, because by my count, this is the one that has just happened. And also the third one from now, when we work out anthropic CFT duality. And there are many other deep and interesting questions, like I think topology change, which likely other people will talk about, which is probably the second one from now. But for the next one, I had something much more prosaic in mind, and it overlaps with some of Juan's comments, which is that it continues to, I think that we still have much more to learn about gauge theory, quantum field theory, and its connection with string theory. I think we have as much to learn as we learned from the last one. And the indication that we really need new concepts is the fact that we still, though we have all of these field-field and field-string and string-string dualities, we have no idea how to derive them. And this is really bothersome. I mean, there are these simple models like Ising where you can derive them. You can take the path integral for one theory and find the change of variables that turns it into the other. And large N vector models where you start with the large N theory, you introduce color singlet auxiliary fields, you integrate out the colored variables, and there's your effective colorless theory. And naively, you might have thought that something similar would work to get, for example, the gravitational and string variables from strongly coupled Yang-Mills theory, and it hasn't worked. Maybe we just haven't found the right change of variables. Maybe it's that boring. Although even finding the right change of variables, I think, would be very powerful. For example, it would enable us to talk about local physics in the bulk theory, which clearly is something we don't know how to do now. And I think if we figured out the change of variables for one ADS CFT, it would tell us what the change of variables is for many, many other examples that we don't know now. But the fact that we haven't found it really suggests that there's something conceptually new, some new way to look at quantum field theory, something we're just missing, and I think it should be there. This situation shouldn't hold forever. You know, right now, our approach to duality, and this is credited to Tom Banks, and I'm sure other people have said it, the way duality works, the way you test a duality is you spend 5 minutes trying to prove that it's wrong, and when you fail, you just assume it's right. And there's great truth to that, because after all, the assertion that a 4-dimensional gauge theory and a 10-dimensional string theory are the same is so bizarre and dramatic that if it were wrong, it would obviously be wrong. And so when you hear about this, you make a list of the reasons why it's not true, and then you think about it a bit, and then you realize, yes, that one guy is pretty clever, after all. And then you go ahead and use it. It becomes part of your bag of tools. But this shouldn't hold forever. I think the situation is similar to things like the Riemann hypothesis, where it's a surprising connection between different things. And I have to say, as a physicist, that a connection between gauge theory and gravity and quantum mechanics is deeper and more interesting even than a connection between analytic functions and prime numbers. But it's a deep connection which you can't either prove or falsify. And that really points, as it does with these great conjectures in mathematics, to missing concepts. So I think that they're out there. Are the hints out there in the literature already? There's integrability, twistors, matrix models, loops. What else? Anyway, it's probably none of the above. DLCQ, who knows? Maybe it's some mixture of these. Maybe it's something totally else. Anyway, I don't think this is a problem. But having, I should say, that having the solution to this problem, again, it would, I believe, contain the answer to things like locality in the bulk, the question that Juan raised of the duals to all of the ADS4 points in the landscape. Also, we have evidence for many things that are like quantum field theories, but are not quantum field theories, like little string theory and non-commutative field theory, and many others we haven't even categorized yet. I think there's a very large space of these things out there, and perhaps if we find the right principle, we can identify this space. Anyway, I'm not recommending that you go out and try to prove this, because you'll surely fail. It probably won't yield to a direct attack, but some random walk sneaking up from behind. But okay, that's where I do think that at some point in the future we will know how to derive these dualities, and I think perhaps it's a step that we need before we answer some of these harder and more conceptual questions that we'd also like to answer. Thank you.
Our next speaker will be Nadi Seiberg.
First, like everybody else, I want to thank the organizers, and especially the organizer of this panel for inviting me to talk here for 5 minutes. I'm really very glad that he didn't ask me to talk for 15 minutes, because I can hardly fill the 5 minutes. The fact is that I have no idea what the next revolution will be. We were posed the question that we have to commit ourselves to the next revolution, and I really have no idea. So I'd like to summarize some of the questions that we should be thinking about. And unfortunately, since my name starts with S, many of the other questions have already been posed by others. But I'll have proof that I thought of them earlier. For some reason, the $64,000 question, nobody mentioned it. Maybe everybody thought he knows the answer to that. Maybe one knows the answer to that. So what is string theory? And it's true that in a sense we are like in the Bohr atom. We have some simple examples. We don't know what the rules are. We certainly don't have a Schrödinger equation. Another interesting question that has already been touched on is the nature of space-time. And I'll say a lot more about it later. In particular, I'd like to focus later in the talk about the origin of time. There's a whole circle of questions that we know very little about, which really circle about the Big Bang, wave function of the universe, how to select the vacuum, this proliferation of vacua, Big Bang, cosmology, black hole singularities. And the fact that we don't understand all these questions, we really circle around the same set of ideas, I think should stop us from making premature decisions about the direction of how physics should work. We don't understand these questions, and one day we will understand them, and the solution will not necessarily involve arithmetic principles and so forth. This is a very conservative East Coast point of view.
Red state.
I actually come from a blue state. Of course. Sorry? As we have heard from Nima earlier in a very exciting talk, it's, I think, quite likely that the next revolution will come from LHC data. There will be a lot of data, and I think we should all be thinking about how string theory should make robust predictions for LHC physics. For example, even before we get to the details like predicting the mass of the top quark, does string theory really predict high-energy supersymmetry or low-energy supersymmetry? That's a question we would like to know the answer to. So we have touched here on two phenomenological connections we can have. One is the connection to cosmology, the other to LHC, and the third is astrophysics. Maybe there will be some signal from the sky that will tell us that string theory is right. Conversely, instead of making predictions, perhaps these ideas will guide our thoughts. The next topic I'd like to talk about is emergent space-time. Many of us believe that the fundamental formulation of the theory will not include space-time. Space-time will emerge as an approximate classical concept. Only when we have macroscopic dimensions can we really talk about space-time. We've already seen several examples of that. There are two matrix models which show that. Both the BFSS matrix model, where space-time is not manifest and it emerges, and the other matrix models of low dimensions, where space arises in a totally different way. In the ADS-CFT, one space direction also arises, and yet in another way. And in non-commutative geometry, there's yet a totally different story. So not only does space arise, space can emerge with different mechanisms. However, what I said about space does not apply to time. Various puzzles with space-like and null singularities suggest that time is also just merely a classical notion. At that point, I would like to ask the following question: what does it mean that the dimension arises? So imagine we don't have space-time in the original formulation of the theory, and it will emerge only in the macroscopic limit. It's not clear what macroscopic means if we don't have space-time. In other words, we should be able to formulate in the original theory what we mean by having a large dimension. How do we do that if we don't have dimensions? I'd like to say a few words about emerging time. I don't have anything useful to say about it except to share with you some of the confusions and why it's not easy. First, it's not clear how one should formulate a theory without time. Especially a theory like physics. physics describe making predictions. We would like to make predictions. We do a calculation. We make a prediction about what the outcome of the experiment will be. How can we make predictions before the experiment is performed if we don't have time? More generally, how do we have causality in a theory which does not have time? How can things evolve without time? Physics is about the evolution of things. We formulate initial conditions and we calculate what comes out. What does it mean that the theory is unitary? Talk about unitary evolution. If we don't have fundamental time, what does that mean? And of course, what do we mean by a wave function? Now, we know that string theory has some non-locality built into it. The simplest way of thinking about it, the string is an extended object. We are familiar with that from T-duality and from all the other dualities. The theory is not completely local. And that's okay if space will emerge. But should we really want something which is non-local in time? That I find really mind-boggling. So all that shows that we're ready for a new revolution. I think we're ready, but what we really need is a new idea. I don't know what the idea is, but I am optimistic that it will come soon. Thank you.
Ashok, Sen will be our next speaker.
I'm supposed to talk about the next superstring revolution, but as we all know, one thing about revolution is that is common to all revolutions is that it's very hard to predict. However, if I am forced to predict one thing about the next revolution, it is the following. And most likely when the next revolution comes, we shall probably be laughing at our present attempts to predict the revolution. Nevertheless, we have to go on, and at this stage, each of us must try our best to bring forth the next revolution. And the best we can do is to work on aspects of string theory which we find interesting without necessarily worrying about its immediate physical consequences, although it will certainly be good to have explicit physical consequences. And the hope is that if a large number of us explore sufficiently diverse aspects of the subject, then perhaps one or more of these attempts will lead to the next superstring revolution. So what I'll do in view of this is to mention some of the aspects of string theory which I find interesting, but I should add that none of these questions are new, and of course this is not a complete set of questions that I have about string theory. Okay, so since landscapes have been mentioned quite a bit, let me begin with the landscape. And if it is true that multiple de Sitter vacua exist in string theory, then the idea of landscape seems to be unavoidable, at least in classical string theory. But one would like to ask, what about the quantum theory? Because by the very construction of the landscape, there is no single observer that sees all the vacua inside all the bubbles of the landscape in which various vacua are realized. But quantum theory is usually formulated from the point of view of a given observer. And so one might ask, how can we describe the quantum landscape from the point of view of a single observer? And presumably, it's only when we are able to describe a quantum version of this landscape idea that we will be really convinced that landscapes are there to stay. Well, another issue which we might worry about is what was before the landscape. In particular, does string theory avoid the Big Bang singularity, or does this question even make sense in view of the fact that time itself may not be a meaningful concept in string theory? And it's also perhaps true that if the idea of landscape is right, then the answer to this question will most likely not have any physical consequence for the present day observation, because whatever happened at the time of the Big Bang will be completely washed out by the landscape that is between the Big Bang and the present era. Nevertheless, I hope you will all agree that answering this question will undoubtedly be important for our understanding of string theory. The final thing I'll like to mention is the role of non-locality in string theory, and this again has been mentioned by several of the speakers earlier. Usually, when you try to formulate a local quantum field theory, it can be formulated in terms of a set of local degrees of freedom. And so there we have this nice situation that we begin with a local classical field theory and then quantize it. And this makes it clear that the theory is local, even though the theory may contain complicated non-local objects like solitons, etc. Well, string theory has no such formulation, even though the quantum theory seems to satisfy all the nice properties expected of a local quantum field theory. In particular, if you look at the classical effective action that arises in string theory and classical string field theory, both have infinite number of derivatives, and as a result, we cannot talk about any classical limit of string theory in which the initial value problem is well defined, for example. Okay, and this is one thing which we would like to have if we are trying to start from a classical theory and then go on to quantum mechanics. And one might ask, does this apparent non-locality of the theory have a deep significance? Is it in particular related to the holographic ideas in string theory? And perhaps a clue is already hidden in the structure of higher derivative terms. Also, these are some of the questions which interest me, but there are certainly many more. So I hope that we will all explore them and try to sow the seeds of the next superstring revolution. Thank you.
Our next speaker is Eva Silverstein.
Okay, so look, our basic job is number one, to find the fundamental degrees of freedom of the theory, find out how they're related to space-time, and see if we could ever look at them, see if we can find any observational consequence that we can connect to them. Now, these grandiose questions are, of course, impossible to answer as posed, so I'm going to instead share with you a few of the steps on my particular random walk that I think are related to these questions, maybe aren't thought about as much as they might be, and might even be accessible. So one question I have is, why do we fixate on matrices? I mean no offense to our esteemed session chair, who has used matrices to great avail. But let me say the specific reason why I wonder about this question. If we look, for example, at the landscape, but we don't worry about all these phenomenological issues, we look at one of the abstract questions that we might be able to answer first, namely this question which Joe also raised and Juan, of formulating these backgrounds. So if you look at the estimates for the number of vacuum and the degree to which we expect to tune the cosmological constant, you translate that into an entropy in the sense of Gibbons-Hawking or Susskind-Witten, and you get a prediction that there should be backgrounds with a number of degrees of freedom scaling, like some integer quantum number to a high power, let's say q to the b, where b is some topological number that can be very large. And as Frederick reviewed so nicely this morning, this is something that we can establish in this landscape. So that's not a matrix-like expression. Maybe something like string junctions address it, but that just raises more questions than it answers. And this has already been seen at the level of the M5 brane in its n-cubed entropy, but I think it's a much more general thing that is suggested by recent developments. So the second question was relations of these degrees of freedom to space-time. This question of unitarity has been raised and is very interesting. I want to discuss a couple of aspects of it. One is there's increasing evidence that we can find and expect to occur processes which can do dramatic things like split space up into disconnected components. In that context, it's very interesting to ask how to formulate the theory and what unitarity means and should we expect it to hold. And these issues of space-like singularities and what unitarity might mean in that context and whether it holds are also great questions, which have been covered by other speakers. So let me just reiterate the interest of these questions. I agree with Nati that we should not jump to conclusions in answering them, but we should push forward on the technical steps that we can see to take, and I think we can see quite a number to take on the subject. Okay, now I'm going to really embarrass myself with this third question. Is there any chance for a signature that we can find to connect the theory to observation? Now, already at the conference, a number of interesting corners of the theory in which specific signatures exist have been discussed, such as I've listed here. But there's obviously no top-down general prediction for any smoking gun signature. One thing I'd like to think about more is whether there could be astrophysical signals. I think Petr Hojava has thought about that recently. And here's a fun estimate, which might mean absolutely nothing, which is that if you consider one of these very quantum gravitational processes where curvature, energy, topology can change, and that energy that used to be in some curvature, some handle, say, can be liberated, then the energy in a gamma ray burst translates into curvature energy scale of order 10 centimeters. So it's not an outrageous scale one way or the other, and it will be fun to see if there's any reason signatures like this or signatures from other sort of compact objects could be accessed. I should say that my phenomenological friends tend to laugh at our habit in string theory of having these big sessions where we sit around and talk about our feelings. Hey, Nima. So they can take particular joy in laughing at that last transparency. So let me stop there.
Our next speaker is Andy Strominger.
Okay, like my predecessors on this panel, I realize it's very foolish to try to predict what the future of string theory is going to bring, but I would disappoint you all if I just came out and said that. So what I'm going to do instead is confess what I really think. Well, it'll excuse me for telling you my feelings, but it will also provide Ashok's plenty of material for Ashok's laughter at the next Superstring Revolution. So there are a lot of interesting problems, conceptual problems in quantum gravity. Black holes we still don't understand. There's the information puzzle, the entropy of Schwarzschild, the quantum formulation of de Sitter space. I think there's no obstacle within the context of string theory to solving all those problems. I think there's no obstacle within the context of string theory to solving all those problems. Okay, I think there's no obstacle in the context of string theory. Here? Okay. All right. Okay. There's no obstacle in the context. Is that good?
Why isn't this working? Can we try one? Do we have another mic?
I can shout. Talk. How's that? Is that good? Okay, but now I can't move? How am I going to talk without moving? Okay, so there's no obstacle, right? There's no obstacle in the context of string theory to solving all these problems. We've made good, continuous progress on them for the last 20 years. I think right now there are interesting things that Juan talked about last year at Strings, and that I think Nadi's talking about, ideas, non-singlets in the C equals 1 matrix model, that I think may give us very concrete handles on that, and I think we'll solve it, and it will be extremely exciting. I think the notion of time is going to go the same way as the notion of space, and again, I think that's something that we'll be able to understand very concretely in string theory. And indeed, in Eva's talk, we heard some ideas about how to deal with singularities and interesting space-like singularities, and interesting things happened with time there. And of course, without time, you can't have a Schrodinger equation, and without a Schrodinger equation, you can't have quantum mechanics. And so that's a really big and interesting adventure that we all get to go through, I think, in the next few decades. There's been a really exciting and gratifying synergy between mathematics and string theory, and I think that that will continue to grow, and in the future it will become more, and the line between physics and mathematics will become more and more blurred, and eventually all interesting mathematics will be found to have realizations in the physical universe. Now, I was going to refrain from saying anything about the anthropic principle in the landscape, but I couldn't control myself during Nima's talk, so I wrote another transparency. So, I have no logical objection to the anthropic principle. It could be true that there are some things we can't explain anthropically, but it just doesn't look to me like we're going to learn anything interesting. It's just going to be a lot of talk, and there'll be there's just nothing interesting going to come out of it. Now, on the other hand, string theory has a habit that whatever question you ask, whatever you work on, you get an interesting answer, but it's often not the answer to the question you were asking. And I think with all these intelligent, hardworking people working on the landscape, something very interesting is bound to come out of it, but I don't think it's going to be an anthropic explanation of the constants of nature. Okay, now this is probably a minority opinion here. I think that amazing surprises will appear at the LHC. Nobody will... I hate to disappoint you. But all sorts of amazing surprises will appear at the LHC. Wonderful things will happen, including a Nobel Prize for Nima. and sorry, Amanda, a lot's going to be learned about nature. It's going to be great fun. But there's a lot of orders of magnitude between the scale of the LHC and the string scale, and I think the odds are against us. They aren't zero, but I think the odds are against us that we're going to learn something really significant about quantum gravity or string theory at the LHC. Not to discourage anybody. On the other hand, I think the odds are with us that sooner or later, quantum gravity will become an experimental science. And I think it will come about through some as yet unforeseen development. For example, I like very much what we heard in Joe's talk about the cosmic strings up in the sky. Now, he used to assign that a probability of 1 out of 8. I don't know what the latest figure is. But it's something that we weren't really thinking about, but it's a possibility. Somewhere out of left field, we find a way of verifying the theory. A few years ago, there were exciting tabletop experiments of measuring gravity at the sub-millimeter scale, which also potentially, but could have led to something very interesting. And sooner or later, we'll get there. And when we do, we'll all be heroes. But also, I think that string theory will turn out, I think it's presumptuous. It's always struck me as presumptuous to think that with string theory, we've got some large part of the whole story of our universe. I think that string theory, but on the other hand, it has too much going for it not to be some part of it. So I think that in the end, we'll realize that string theory is a small corner of the real story, but a really important and really interesting one. And then the fun will begin. Once we've got experimental realization of string theory, I think there will be a whole new realm of questions that, with our new experimental knowledge and understanding of string theory, that we can start to address. Let me stop there.
Now I get to put my 2 cents in. I had some transparencies, but after Andy showed his, I couldn't bear to show them to you. So, is this on? Does this work? Yeah, this sounds good. All right, so I guess I just want to take a few minutes to share with you something that bothers me about the state of our subject. And I know it bothers a lot of people. Juan mentioned it. Well, when I started working in the subject, which by now is a lot of years ago, there was the most amazing sense that quantum gravity was special and unique, and it took delicate, miraculous mechanisms to unify quantum mechanics and gravity. And it was really exhilarating. But that sense of uniqueness and distinctiveness has receded. We've learned from the ADS-CFT correspondence that any conformal field theory, like the three-dimensional Ising model, defines a quantum gravity. It's worse. Any field theory, because at short distances it's conformal, defines a quantum gravity in asymptotically ADS space. And it gets even worse. If you consider D0 branes in a brain bulk duality, you find old matrix models or matrix theory. These are just quantum mechanics. You can take ADS-CFT and cut it off in the ultraviolet and the UV, and you get systems with finite numbers of degrees of freedom. We are heading toward the point where any conventional quantum system describes a quantum gravity. That's disturbing. Okay? That's a very large set of quantum gravities, and we need to figure out a way to handle it. Does the basic equations that we're eventually going to have to work with, can they talk about every quantum system you write down? Is that the way it's going to go? Or is it that when we think about something like cosmology, where you start from a Big Bang in the right way, you only have to think about a small subset of these possibilities, or maybe none of them at all, because all of these subsets, time is a nice continuous parameter, and in cosmology it won't be. So that's what bothers me. What do we do about this proliferation? What's a manageable set of degrees of freedom that we can talk about and think about in a quantum gravity? And I don't know the answer, but I think we should think about it. So with that, I'll end this panel discussion, and we're now going to try to open it up to the audience as a whole. Now, this is going to be complicated because of logistics. I think what we are going to do is that there are mics, one on each aisle down here on the main floor, and one on this side. Is there any mic up there? Yes. All right, so at some point a mic will appear upstairs. And so if people want to make comments, which I hope you do, come to one of those microphones, or we can maybe pass this one around. Hold on just a second. Okay, so let me invite you then, anybody that wants to make a suggestion about ideas that we should think about for the next revolution, comments on anything the panel has said, All right, Mike, do you want to go to that mic? Other people that you're interested in, Lee? Okay. Why don't you wait first? You'll be second.
Okay, I'll say I have three things to say, which to some extent amplify on what the speakers have already well expressed. So, I don't know, three ideas about what revolutions there might be to come. So, one is this question of the vacuum selection. I actually wrote in the proceedings of the 2001 Lesuche School that the foundation of this third revolution would be the vacuum selection. And the reason that I wrote that was looking back at the duality, the second revolution, and at least at Rutgers, the group I was in, there was this very clear sense that non-perturbative effects, non-perturbative understanding was the problem. We have to address this, and lo and behold, it actually got addressed. So it was very gratifying, and it seems to me that in terms of the problems we would desperately like to solve, this is the number one. But as will become clear in my talk tomorrow, I think it's just a hard problem, and to the extent that it can be addressed, we are on the way. It could be that this is already this third revolution that's just much more agonizing and slow motion than we might have hoped for. So then a different idea that, just a totally different idea about where things are going. I think any of us should stop and reflect and compare the state of string theory and even the standard model, which is our gold standard, with the Schrödinger equation of atomic physics. It's not just quantum mechanics, which is certainly beautiful, but even just that Schrödinger equation of electrons and nuclei is actually really quite a bit simpler than the standard model, and it's certainly quite a bit simpler than almost all formulations of string theory, although the BFSS matrix model, the pure N equals 4 super Yang-Mills ADS-CFT might be the only ones to rival it in that simplicity, but of course they are not complete so far as we know. They don't describe the realistic cases. And of course our condensed matter colleagues never tire of pointing out how not just that these Schrödinger equations are beautiful, but they contain almost all of the physics that we ever see. But they are beautiful, and I think it would be disappointing if string theory at the end didn't turn out to have a comparable simplicity and beauty. And I really do think both that the formulation and some description of this immensely complicated landscape of solutions can be written down and will not take much more than one page to write down when we really understand it. And that's one of the things that keeps me going, I think, is the ultimate goal of a lot of this study of the landscape. But when you think about the complexity of the structure and the mathematics that must enter in that description, you realize how far we are from this. And so I don't think this is going to be the third revolution. This is going to be the fourth or the fifth revolution, something like that. And so that leaves me at more or less the beginning here, which is that we have an obvious third revolution coming up, which is the experimental revolution, we hope, of discoveries of the coming years. And I think we've actually done amazingly well with, for 20 years with very little experimental input, and it's asking a lot to keep pushing along that way. And so I'm grateful that we'll have further, I very much hope we'll have further input from that direction. I think that will be the revolution of the coming years.
Thanks. Do any people on the panel want to comment? Okay. I'm sorry? Oh, to threaten them, you mean? I see. All right. Lee, you wanted to say something. Go ahead.
Yeah, I would like to say a few words for background independence, which I don't know if it will be the next revolution, but I'm fairly persuaded it will be the last one. Those of us who think about quantum gravity from a background independent point of view understand that background independence has a long history. There's a long story in which general relativity was and is understood as a step of physics becoming more background independent. And quantum theory is a step in which physics becomes more background independent. There are precursors, which is a whole historical discussion to discuss. And so it's natural that the thing which brings together those two theories is even more background independent. Some of us who go back to 1984, when string theory when there was all the excitement about it, immediately came to the conclusion, this is great, and I agree with Andy, this may very well be a big part of the symmetries and the dynamics that underlie nature, but it needs a background-independent formulation. And one hears through the 20 years since people saying from time to time, for example, Nadi here asking these questions about emergent space-time, or Guri, the first talk, we need a background-independent formulation. This is a consistent theme. Now, some of us set out to do that, and the result was loop quantum gravity. Loop quantum gravity emerged from attempts of Lewis Crane and myself to make a background-independent formulation of string theory. The other big background-independent approach to quantum gravity, which we call causal dynamical triangulations, emerged from Amborn and collaborators' attempts to solve the problem of going beyond the C=1 matrix model. So there's the task. Nobody has yet made a convincing background-independent form of string theory, but the challenge has been very fruitful. Now, the result after 20 years is that there's been a lot of success. For example, Nadi, there are well-worked-through examples of space-times emergent in both programs. For example, Friedel and Levine, or Amborn and Lowell recently, these are detailed models where one can see it happening. And there are also persistent unsolved problems. And I think, sometimes this is mischaracterized as some sort of rivalry, but I think what it really is, if we think clearly about it, is it's a tremendous opportunity. It's what you would want. If everybody agrees that sooner or later string theory has to have a background-independent fundamental formulation, or the fundamental theory which may, as Annie says, include some parts of string theory. And meanwhile, there's developed a rich set of examples and studies in which one can see in detail what kinds of ideas work and what kinds of ideas remain open and problematic. It's a tremendous opportunity to take that richness and try to understand how it may fit with the richness which has been uncovered in the same 2 decades in the context of exploring the ideas about supersymmetry and string theory and so forth. So I think it's there's a lot to do, but I think that the results show that there are quite a lot of examples, lessons, starting points, and we invite you to come and think about background-independent physics with us. Thank you.
All right. Do you want to make a comment?
I think we're okay.
You're okay.
I was going to go back to something that you said. You raised it as a problem that, in some sense, it looks like every quantum mechanical system has a gravitational interpretation.
Yes.
But I think that's if it's correct, it's probably an important change in point of view. It recasts the question of searching for background independence as a question of, well, I don't think this is a whole story because the quantum mechanics only arises in the spacetimes that do have asymptopia. I suspect part of the answer to some issues that Raphael raised, for example, is that quantum mechanics, as we know it, only works in the cases with asymptopia. And what's inside is more murky. Some speakers touched on that. I can't summarize everyone, I'm afraid. But if we limit ourselves to these cases with asymptopia, it's plausible from what you and Juan and others said that every quantum mechanics system has some dual interpretation. And then the issue is, which very special ones correspond to macroscopic spacetimes? And that seems like, although I don't have a glimmering of the answer, it still seems like a very deep reinterpretation of the question. And a cautionary tale for discussions like we're having tonight about predicting the future. Because had we had this discussion 10 or 20 years ago, or even longer, the search for a fundamental explanation of what string theory is, background independence and all that, would have been central. And it's clear that a priori thoughts would just not get anywhere. We would not have gotten to what looks like a deep reinterpretation of it if we had too much of a preconception about what was supposed to happen.
Well,
Sorry,
let me make a quick...
little bit of a wander.
No. Let me make a reply to your remark. It seems one of the things that disturbs me, and maybe disturbs Juan, or maybe not, is that the notion of macroscopic space-time is kind of a quantitative and not a qualitative notion. It's kind of like the difference between liquid and gas.
What I really would suspect
Yeah.
is that space-time is only precisely defined when there's an asymptotic parameter. In the limit, as n goes to infinity or epsilon goes to 0 or
Yes.
something, space-time is a precise notion, and away from that, it is murky.
But I mean, so what do we do with the three-dimensional Ising model?
Well, we need to get whatever insight this reinterpretation would lead us to. But instead of, I'm just saying that you might have, with a slight modification of your remarks, put a more positive spin on it. That there's what seems like a real reinterpretation of the question compared to what we would have asked 10 years ago, or compared to anything we could have gotten if we had too much of a preconception of what was supposed to happen.
Yeah.
Okay. It has to do with the question that Ashok raised. How do we think about quantum mechanics I guess you were thinking about eternally inflating bubbles and all that kind of thing. Okay. So it seems to me we have two different conjectures about the way the landscape gets populated. One of them is that bubbles nucleate in an inflating universe and simply populate every possible or many of the different vacuums. In other words, eternal inflation and bubble nucleation. Another idea that's been around for a long time is the idea of, what is it called, alternative universes, the many world interpretation of quantum mechanics. That the wave function splits and splits and splits and splits, and in that way populates all of the landscape. My conjecture is those two things are exactly the same, that the multiple bubbles of de Sitter space, bubbling, nucleating, and all that stuff, pocket universes, all those words, mean exactly the same thing as the many worlds interpretation of quantum mechanics. Do not expect me to explain what I just said.
Is there any reaction from the panel to those conservative? Why don't you use that mic?
So can we infer from that, Lenny, that you think quantum mechanics is an absolute concept which will survive all future developments?
I think that quantum mechanics, yes, I do think quantum mechanics will survive, but I'm not sure that that necessarily means that time is an absolute concept. But I think that maybe quantum mechanics does have something to do with eternal inflation, bubble nucleation, many universes, and that concept is not really different than the many worlds interpretation of quantum mechanics. I don't think we should have two independent and different ideas about how the landscape gets populated. So I think they're the same.
I just want to make a quick comment after listening to this distinguished panel. It seems clear that if you want to make a significant impact in string theory, it really helps if your last name begins with S.
I think having an S in your name is is partially. Okay. Other people having comments. Do other people on the panel want to talk about this? Do you think that do you want to change your last names? Do you think that quantum mechanics and eternal inflation is the same thing? Well, in the sense that Lenny mentioned. Thank you. No comments? No.
Well, I think what Lenny said is probably clearly right.
Is that the universal opinion of the panel? Yes.
This is in fact the same thing as anthropic CFT duality.
I was going to say something about no credit hogging, but all right. Anybody else want to voice yes or no on this? Do you think it's plausible? I hated it when Lenny first told me about it. That probably means it's right. But Well, I can't remember why, but there was a good reason. Yeah.
Well, I think there is some evidence that it's right. That if you Linde et al. With this eternal inflation calculate these probabilities that give the same as what Hawking gets from the wave function of the universe, that is how you would imagine it from this other point of view. So I mean, there is some evidence that this idea is correct.
I have to confess I don't have the foggiest idea what Lenny means. So if we put Lenny in a box in place of Schrodinger's cat, I would have thought we ended up with two worlds where we were in this part of the landscape with Lenny alive or Lenny dead. But is he claiming that we end up in some other part of the landscape? I mean, they seem to have absolutely nothing to do with each other. What are you talking about, Lenny?
Okay, so there's another Lenny someplace, right? Someplace far, far away in some other bubble universe, there's some other Lenny who's doing exactly the same thing as I am now when you put me in the box. And that Lenny will survive this. Well, this Lenny certainly is not going to survive, I can tell you. Not for too long, or much longer. Yes, so decoherence. That's one thing which is clear in an infinite landscape, that everything is replicated in this way. On the other hand, I also have the suspicion that the multiple replications of things is a kind of gauge redundancy, so that there really are. I see Joe nodding his head. I think he's falling asleep.
Somebody, nobody's at these microphones. Who else wants to say something?
I think it's clear that those of us who are around for the first revolution are not going to be the ones leading the next revolution. So it's just a challenge to the young people here to sort of, pick up the challenge and tell us what to do next.
I came all the way from Waterloo, Iowa to tell you guys something you don't know about theoretical physics. So the first thing you have to do is forget everything you know about theoretical physics and string theory and all that stuff. Because I think there is a simple way you can understand 11-dimensional universe drawn on a piece of paper. And if you let me use the overhead for just briefly, I'll try. Okay, well, that's fine then. Well, I'm sorry.
Thanks. All right, so let's sort of get back on track here. Why don't you go to that?
I have one comment and one question. In the former Soviet Union, how to make a revolution was a canonical subject of study for many years. So I didn't escape when I was a student. So there are 55 volumes of Lenin about that. And I don't want to repeat all these contents of this. But the basic message down to earth was that revolution cannot be made on demand. There should be conditions fulfilled, both from above and from below. Those who learned about that, they understand what this called. It's called revolutionary situation in canonical textbooks. So I'm afraid that...
Do you have some concrete suggestions for the field then?
Let me finish. What I'm saying basically is that maybe it is not very productive to talk about evolution, better to talk about conditions. But my question is a little bit different nature to the panel. String community is a part of physics community, and when I say 10 or 15 years ago, when I was awakened during the night and asked, why string theory? The answer was very simple at that time, that the superstring theory provides, the renormalizable theory of quantum gravity, and it has no adjustable parameters, so in principle everything can be described. This was an old answer 10, 15 years ago. And today it's becoming increasingly difficult to argue the case of string theory in physics community, because physics community is very pragmatical. They want some, so to say, some outcome. So come back to the same question. Why string theory today? How we will put it in a short answer to this question? Of course, in this audience, there is no need to argue the case of string theory. But outside of this audience, I think there is a need.
Okay, fair enough. I think we have the idea.
Yeah.
Does anybody want to give a few-word reply? Well, all right, I'll then, assume this difficult job. I think it is the only consistent theory of quantum gravity that exists, and it is and so I think that by itself justifies its continued study. So maybe, all right, so, okay. Yeah, right. Right. Well, that's a fair comment, and that's the kind of thing that most of us in the field want to not think about. So, but it's a fair comment. I mean, it's been 20 years, and 20 years was the time between Einstein's photoelectric effect theory in 1905 and Heisenberg's, writing down quantum mechanics, and we haven't done as well. So there is an issue. Do you think we've done better?
To do except just hope that the Bush administration will keep paying us. That's all. We get religion. No, I have nothing to say. Why did you give me the mic?
Do you have something coherent to say?
Yeah.
Oh, okay. Is that my board? I don't want to keep this on.
Oh. No. I don't. Well, first of all, I don't think we should be arguing the case for string theory. I think we should just be explaining what string theory is, and then people can decide whether they want to work on it or not, and whether they want to fund on it or not. And there's lots of good reasons for not putting your money on string theory, and there are reasons for putting your money on string theory. I don't think we should feel we have a mission to convince people, and in fact, I often think it's the other way around. I mean, we get all kinds of, at Harvard we have all kinds of graduate students and undergraduates that think that we've already solved all the problems and that everything is wonderful. So I don't think we have any need to argue anything for anybody. What we have a need to do is to understand the truth about the mathematical structure of string theory and about our universe and how they're related. And I also don't see the cause for this pessimism. Things are not going fast enough, and what are we going to do? We've been 10 years without a revolution. There's been all kinds of interesting things happening. It seems there's two kinds of states in the field. One is where everybody says nothing's happened for a long time, and the other is where everybody says all the interesting stuff was just done and there's nothing for me to do. We've made spectacular progress in all kinds of directions that we couldn't have imagined, and those who want to join us can, and those who don't have to. But I think it's a wonderful, exciting field, and there are many problems to work on, and there are many concrete things to do. And I think at this conference there are a lot of really interesting talks, and people are doing interesting things, and they will lead to places that we haven't imagined yet. So I don't see the cause for pessimism, and I don't see the need to sell ourselves. We just.
Can I?
Wait a minute, I think some people want to respond to this. Peter, why don't you go to that mic there? I think you're supposed to leave that one in the.
These last few comments reminded me of something that happened long ago. The first conference I ever went to, a big conference in Geneva of the Rochester type. if you haven't heard of Rochester Conference, anyway, those were the conferences to go to. And again, at an odd hour, it was on a Sunday morning. I remember when the experimentalists were doing their excursions on the lake, the theoreticians all assembled in the great hall at CERN, because Jeff Chu decided that regipoles, which ultimately led to dual models, which ultimately led to strings. So and the word he used was revolution. He got Heisenberg, no less, to endorse him, that it is a revolution. And the Russians, talking of this comment, were there, but they were not Russians, they were Soviet scientists. And these were not the scientists that were really invited, these were the scientists that were sent. And the funny thing was, after all of this talk about revolution, which involved a lot, mostly potential scattering, in which you had regipoles and they used the method of Yost functions, Race Yost, a Swiss axiomatic field theorist who had a very good and very dry sense of humor, said, I really like this stuff that you are all doing, and it's really very worthwhile, and it's very cute. But let me tell you, and with the Soviets in the president for this, they could have had problems. Here in Switzerland, we have long stopped to believe in revolutions. So I don't know. Maybe that's the alternative you had in mind.
Go ahead.
I just wanted to add a comment following what Steve was saying about the history of quantum mechanics. One thing that's completely obvious, I think, is that there was something like 24 years between Planck and the year before Heisenberg. And if we'd had a panel like this, if there had been a panel like this who were trying to predict what the next great advance in quantum theory was going to be in 1924, they would have missed it by a million miles. There was no hint whatsoever of what was about to hit them. There was a young, unknown graduate student who was certainly not on such a panel, who came up with ideas which were so completely different from everything that had gone before that just a very short time before the theory was formulated. So I'm not sure whether there's any lesson in that, but at least there's some hope, perhaps, that some young person here will produce something totally unexpected.
It's fair enough. I'm sorry?
Hello?
Yes. Okay, we have a speaker here that needs to speak.
Okay.
Go ahead, Martin.
It's okay. Actually, maybe this is in the spirit of some of the other comments, in the sense that I have some questions which are really not very revolutionary, but there's one particular thing I'd like to ask. Something that's struck me by its absence is no one has discussed, and maybe the answer is obvious, whether string theory has anything to say about neutrino masses. I mean, that's obviously a field where we have data, and maybe the answer is simply that's really a problem in field theory, that's too low energy, and there's no useful input from string theory. I'm asking genuinely. It's not a rhetorical question. So maybe somebody could answer that. Another question, which is, I think, less mainstream, but there was recently some work by Kolb, Matarese, Notari, and Ryota based on older work by George Ellis, where they proposed that the nonlinearity of general relativity may imply that the interpretation of the cosmological parameters is too naive, since we always use homogeneous, describe the universe as being homogeneous. And I'd like to know if anybody has any comment on that.
It's wrong. Yeah.
Wrong, but it's all just rubbish. Okay, that's good enough. I was. And then I guess I wanted to add, to chime in a little bit on some of the comments about history of quantum mechanics, as maybe a little bit of a warning, which is there's one subject that has a long history, which started early on in quantum mechanics and continues to this day, and as far as I know, has produced almost nothing useful in physics, and that's the subject of interpretation of quantum mechanics. And I'm worried. I worry if maybe some of the questions that people are raising are in the same direction. But I would really appreciate the question about an answer or comments on the neutrino mass question.
Okay. All right. Does anybody want to comment on any of that?
Well, David Deutsch's proposal to make a quantum computer, which is not becoming a technology, came out of worrying about the problems of quantum mechanics. Just to repeat it, David Deutsch's proposal to make quantum computers, which is evolving into a real technology, came out of wonderings and thinkings about the problems of foundations of quantum mechanics. So I think one can hardly say there's not been a fruitful outcome. One could have said that 10 or 15 years ago, but not presently.
I can speak to answer the neutrino mass question. There was a recent conference in Munich of the string phenomenologists, and there was reported a work by Langecker, Kane, two others, Liantel Wang, somebody else, who analyzed this in a sort of non-systematic way in heterotic string compactifications and enumerated hundreds of them to try to see if they could reproduce the neutrino masses. And they found it was surprisingly hard. They actually found that out of this small sample, no models worked. So they felt this was a serious test.
Can I go ahead from up here?
Well, I have a fairly mundane question. I think a couple of years after the duality revolution, if there was a panel like this, one of the central questions would have been, what is M theory? And that question was not mentioned by anybody on the panel. I don't think anybody actually used the words M theory rather than string theory. And of course, the matrix theory was an attempt to try to find out what M theory was. There seems to be kind of a movement away from the idea that understanding M theory as 11-dimensional theory with M2 brains and M5 brains is going to give us some kind of a unified way of understanding something about string theory. It's been replaced by ADS-CFT, more general ideas of gauge, gravity, duality. But there are many, many things that we don't understand about M theory, and I was just wondering whether people on the panel think that those questions are not really central to making, further dramatic progress, or have they been subsumed in other things? Or I'm just curious, because it's something that certainly used to be a major focus, and now it seems not to be.
Anybody want to say something?
Well, I think when people say string theory, they mean quantum gravity. Probably we should call our field quantum gravity, and it includes M theory. It's at least.
Quantum gravity regime where we can't use string theory to do the computations.
So I think there's a tendency in our field that any problem that lasts more than 5 years that is not solved is no longer an important problem.
Okay, go ahead.
I'd just like to make a comment going back a bit to what Lenny had said about string theory and where it's going and its impact on things. I've come in from the field of astronomy and cosmology, and it's awesome what we've done in the last 15 years. We're mapping literally, the face of the universe. And in string theory, how that interfaces with astronomy and cosmology, I think is really, really important and significant. Because for one thing, the concept of infinity, when you bring in the mathematics into the physics, is really invaluable. I've had some of the top astronomers in the world trained in Cambridge tell me, well, when we talk about infinity, we don't really mean infinity. It just means far away. And you come into string theory and you come into the mathematics of it, and infinity means infinity. And also, when Ophir was talking about, we just came from Perimeter where we had the summer school, and he's talking about, well, you just go on and on and on. It can go. We're talking about the fabrication of space and time and the infinite potentiality of universes and worlds, and it gives the mind what it does to the fabric of reality, how we can understand it, adds so many dimensions to thinking about reality that I think, just as I'm entering the field, it's awesome, and it's giving the mind.
I appreciate your remarks, but I think we need to move on, so thank you.
Okay.
Anybody else?
I have a question for the panel in the spirit of a previous one from up front.
M theory very beautifully unified different string theories and concurrently geometrized various questions involving different kinds of branes and different kinds of fluxes. There's a principle in mathematics which is that a difficult question in geometry, if it is to be properly understood, must be algebraicized. So the question to the panel is, will M theory get algebraicized?
Anybody want to take that?
I thought it was done by. I thought it was. Was it not done by BFSS who translated into matrices? Sorry.
Okay, can I make? Yeah. I think M theory is just one corner of string theory, and I mean, just like understanding all possible backgrounds in string theory is important, I mean, understanding M theory is also going to be important, but I don't think it means that solving M theory will solve everything about string theory. And M theory geometrizes many of the problems, but nevertheless there are also backgrounds which are not geometric and which cannot be put in the geometric form even in M theory. So it's not that by going to M theory you can make every problem geometric.
I guess the question was, if there is an ultimate non-perturbative formulation, will it necessarily be algebraic? And maybe Juan's answer addressed that.
Yeah, go ahead, Lonnie.
On a different track, I wanted to ask a question about the relationship between the LHC and string theory. So a number of people, when listing what they thought might lead to the next revolution, mentioned the LHC. Andy made a point, which is where he made a statement of his feelings, which was that he felt that it was unlikely that anything we found at the LHC would really tell us about the fundamental questions of quantum gravity and string theory that are the ones we've been talking about in most of this discussion. And I guess the question I want to ask is, to anybody, what is the most optimistic thing you could imagine seeing at the LHC which would really give us a clue as to the structure of quantum gravity or string theory? I mean, just to put that in context, most of the things that people talk about, supersymmetry, the Higgs, as Nima mentioned, may be more or less natural, but they can invariably be put in the context of field theory. And we're having very good success at replicating almost any field theory you can imagine in some string vacuum. So is what we're going to see at the LHC only going to give us more selection criteria for vacua, or is there anything anybody can imagine where it might really give us some hint at a new principle?
Good, thank you. Who's? Or pass go.
Well, yes. I mean, these dramatic proposals have been made, string recurrences, Kaluza-Klein recurrences. If we saw evidence for, anything that looked like another dimension, that would be one of the great triumphs of human history to predict such a thing.
Well, another possibility is that we'll see absolutely nothing, and with no explanation at all of any of the naturalness problems. And that would certainly go in some direction of telling us that we're thinking about naturalness extremely wrongly. So I find the idea that we discover absolutely nothing might in fact tell us more than anything else. Yes, nothing but of course, yes, nothing but the Higgs, that might really tell us something deep about issues of naturalness.
But I guess there's a question that Lottie asked, would that give any kind of distinctive evidence for string theory?
No.
That was a rhetorical. All right, do you guys want to get into this, or are you just drinking your water? And
This is in water, Steve.
That explains it. Go ahead.
Yeah, I always tell these Jehovah Witnesses that come to my door that what they're telling me is total crap because it cannot be falsified. So can you imagine anything in the next 20 years, any experiment that will falsify string theory?
You're not supposed to be asking questions like that. Anybody want to talk about Sky? Well, I can't falsify it. Well, you want to say a word about that? Yeah.
Sure. There are several experiments underway or about to be flown which test Lorentz invariance at the Planck scale. One of the issues is whether there's an energy-dependent speed of light, which is something that string theory, at least so far, in no version predicts. Another is that there would be no GZK cutoff, which again is something which is predicted in some approaches to quantum gravity, but not predicted in any version of string theory, because these would both be effects that follow from either breaking or deformation of Poincare invariance. And those are both, Auger is rumored to be reporting in the next several months. And the next experiment, which is slipping my mind, but the next gamma ray satellite, which measures, has the possibility of measuring energy dependence of the speed of light to a Planck scale sensitivity, flies next year. So those are both, and it would be very nice if there was clear, and I'm very glad Edward is about to address this. Yeah. But it would be very nice if there was a clear statement of a prediction for these experiments from string theory, since there is from other approaches to quantum gravity and the experiments are in progress.
Well, I actually was aiming to respond to about 3 questions ago when we were asked what might come from the LHC that would give encouragement for string theory. Mike gave one obvious answer, which is that large extra dimensions or quantum, or in particular, in principle, string recurrences might be observed at the LHC. But nobody gave the other obvious answer, which is that supersymmetry is an important part of the string theory story. And it would certainly, after all these years in which many of us have spent at least half our time working on supersymmetry, be gratifying if it was discovered. That would seem to be a strong part of, an important part of the response to that previous question. I'm reluctant to comment what was just said about Lorentz invariance, except to say that the arguments in the literature concerning it seem singularly unconvincing. I might say I did in a paper that you can find on GRQC, comment on Lorentz invariance from the point of view of one approach that's appeared in the literature, having to do with the Kadama state.
It's their turn. It's their turn. It's their turn. It's their turn. Yeah, we already more than their way. Other people want to comment? Oh, Michael.
Yeah, I'm actually going to echo, in this case, Ed's comment, and dealing with 2 people I admire here, and not disagree so much with Lenny as sort of say that I think in the one case, if supersymmetry is discovered, this would be, I think, right now most string theory papers, many papers in physics generally start with, well, if you take up your average string model building paper, it will say, oh yes, and we want, in the physically important cases, n equals 1 supersymmetry, or da-da-da. And I have no idea why people say that. Or why, and especially with many of the developments in the last few years, I think the story has become much more obscure. I have a colleague who once said to me, well, string theory hasn't done much of anything, but at least it predicts low energy supersymmetry. This is not a string theorist, this is a cosmologist. And I had to say, well, we don't know. And so I would say on the one hand, it would be very exciting if, we still have, as Nima stressed, we still have, 23 months or whatever many months it is. And it would seem that, having thought so much about this, we might be able to answer this question one way or the other. And I'd say right now that the landscape, with all of the complaints about it, is the only setup which really allows us to focus in any way on this. And maybe there's a better way to think about it, but I predict that that revolution will take longer than 23 months to arrive. And I would say also that if we end up in Lenny's situation, we are going to be, I should say, first of all, even then, and I think Ed and I have had this discussion many times, if we discover supersymmetry, even if we haven't successfully predicted it, I think that would, that will certainly, it will make more sense at least to start out all those papers with that first opening line. And it will certainly, but more seriously, it will certainly be a guide to our thinking. If we fail to discover it, it will also be a guide to our thinking, but of course, and I should add large dimensions or something else. If we fail to make a major discovery of that nature, we will, it will certainly be scratching our heads, I think, in a more, in a more difficult way. That's all.
One thing I find interesting is that in the last several years, the last several months even, a good deal of progress has been made on stuff like topological string theory, topological M theory, mini superspace quantizations, theories where you've carved out some sort of closed subset of the degrees of freedom and said something about them. I think it would be interesting to see in future years what other closed subsets you can carve out, and if there is some way to add back in the degrees of freedom that you've thrown away. Some sort of perturbative way of doing it, even non-perturbative ways of adding these degrees of freedom back in.
Yeah, I think that's an excellent point. I think, when we look back, especially in other fields of physics, one of the main ways one makes progress is to construct simple models, trying to extract the essential physics. And in string theory, that's rather difficult. There are a couple of examples, topological string theory, as you've expressed, these low-dimensional matrix models, but there aren't a lot of examples where you isolate a few degrees of freedom and really handle the system. It will be very interesting to find more. I agree. Yeah.
I have a favorite example of this type of question. So there's a lot of focus on supersymmetry, BPS quantities, and it's a brilliant way to be able to continue from weak to strong coupling. But there is this question of whether it's a good guide to the full physics or not. It's clearly not generic, and so on. And my favorite example of this is dynamics on the moduli space. If you roll scalar fields on a moduli space, even if you know the moduli space metric precisely, if the scalar field rolls toward a point with light degrees of freedom, which was one of the beautiful revelations of the last revolution, if you just focused on the quote-unquote moduli space approximation, the scalar field would fly past that point off to infinity. But if you take into account kinetic effects, particle production, higher derivative terms that are fundamentally non-supersymmetric but are calculable, the result of that experiment is infinitely different. The field gets trapped at the special point with extra light states, the singular point, or it gets slowed down in a big way if there are lots of these light degrees of freedom. So this is a simple example of where the BPS quantity, while exactly calculable, for example, in the n equals 4 theory, is a very bad guide to the physics of even slightly non-supersymmetric generalizations.
Okay, well, we're drawing close to the time we're supposed to stop. I am going to assert my prerogatives as organizer now to satisfy a question of personal curiosity, using you as lab rats. I am curious about the sort of current state of the field in regards to the anthropic principle. And I want to ask you, I guess as a sharp question, do you think that the smallness of the cosmological constant will be explained by an anthropic argument, or do you think there will be a physical argument that will explain this number? That there will be a large landscape and that there will not be a selection principle that simply follows from the equations, but relies on some other sort of environmental. Yeah, does that word, an environmental variable, does that clear?
I want Lenny to use the anthropic principle to predict the outcome of the vote first.
So.
Do you understand the vote?
So we're talking about the year 3000, right?
Yeah.
I mean, another possibility is that it
will never be understood.
That it won't get explained for a long time.
I'd like, assuming that there's an asymptotic explanation where there's a
So we should imagine that we know far more than we know now.
Absolutely. Yes, I'm asking in the future when these problems are resolved, and I will take heart from your optimism to assume that they are resolved. I'm sorry?
Okay. So it is interesting that all the members of the panel most of them kind of did not commit themselves to the next 2 or 3 years. You want us to commit ourselves to 3,000 years?
Yeah, that's my prerogative. Okay. All right. So, well, how can I say
No.
this?
No one can abstain.
I will never talk to you again. But you, of course, you're allowed to abstain. Yeah. What is the third possibility? Well, it is a sharp question, irrelevant or not. So I'd like to.
Oh, no.
No. Come on.
None of the above.
This room, we got a lot of lawyers in here. It's clear. All right, so is it clear? The two possibilities that I want you to vote on are that there's an anthropic, environmental explanation, or there's some physical explanation, some equation you solve and you get this 10 to the minus 120 out of it as a more or less unique prediction. Okay, so how many think there's a physical explanation, an equation? Wow. Holy shit. All right, I'm not going to count it, but that's all right. How many think there's an anthropic explanation? What do you think that is? 5 to 1? Look at the panel. The panel is more. Yeah. These are the people you're going to hire. The last time there was a vote like this, I was at, and this was part of the reason for my curiosity, was at Santa Barbara a couple of years ago.
Yeah.
And I think it was like 25 or 30% for the anthropic principle.
Wait. Oh, this is Sean Carroll's.
Yeah. What? I didn't hear you. What did you say, Mark? Break it down geographically. We'll do an exit poll, okay? This is. I think it looked to me like about 5 to 1, 4 to 5 to 1. Would that be your? Yeah. Sorry? It's over. Yeah. That's right. That's right. The anthropic principle is out of office.
Steve, that's about the same ratio of the majority of Americans who think that humans were made about a few thousand years ago. I really recommend doing science by democracy.
Is that a question of intelligent design? Is that? Okay. Well. You want? So you would like me to take a poll on intelligent design? What does that mean? How many people think God made the universe just for us so we could be here? All right. Is that? No, I've learned what I wanted to know. Okay.